Okay, so Leetcode practice question. So two purposes in this video. The first one is to see how to solve this problem properly, find the solution, and put in some code for it. And the second one is to see how to solve this problem during an interview. What is the interview process for coding? So let's get started. Remember, always the first thing in a coding interview is try to understand the question. If there's anything unclear to you, please ask some clarification questions, and also at the same time think about some edge cases you need to take special care of when writing code. So let's take a look. Alien dictionary. Alright, so there is a new alien language that uses a English alphabet. However, the other among letters are unknown to you, and you're given a list of strings from the dictionary, where words are sorted lexicographically by the rule of this new language, and then derive the order of letters in this language and return it. If the given input is invalid, return empty. If there are multiple valid solutions, return any of them. So, okay, so let's take a look at the first example. We have input words like this, and output is WERTF. So based on the first and second word, we can find that T comes before F, and then W comes before E, and R comes before T, and E comes before R. So if you write this down, it is T comes before F, and W comes before E, and R comes before T. Okay, R comes before T, which forms this part, and E comes before R. Okay, yeah, so that's why their answer is this. And similarly, this one we have ZX, and we have Z. For this one, it is not valid. Okay, so let's see the constraints. So each word is not going to be empty, and the words are, so each word is not empty as well. Okay, and we are going to for sure have a list of the words to be not empty, and the words I consists of only lowercase English letters. Okay, so one thing I think that is unclear to me now is, what if there are only two words? Let's say it is AZ and then the BX. So for this one, of course, we know that A comes before B, but the other for Z and X is actually unknown to us, because of comparison is solely based on the first letter. So for this one, I guess it is saying, so it says there if there are multiple valid solutions. I guess this is what it means for the multiple valid solutions. Otherwise, I cannot think of any reason we have multiple valid solutions. So let's go with the way that if the order of some letters are unknown, then we can have multiple solutions. So something like that. The second one is to find a solution for this problem. So in this part, you communicate the idea how to solve this problem and do some runtime space complexity analysis at the same time. After you get an agreement, then start coding. So for this one, let's see how to solve this problem. So I would say this is more like a topology sorting problem. So regarding the topology sorting, so first of all, we need to generate the graph, and compute the degrees for each node, and then then we do the topology sorting. So the sorting is kind of like well, it's kind of like BFS. starting with it is like starting with nodes with in degree as 0, and then remove, and then update the in degree of adjacent nodes for the removed node. So and then so on and so forth. It's kind of like a loop. So we find the nodes with in degree at 0, then remove, and also at the same time update the in degree of the adjacent node for the previously removed node, and then start to find the nodes with in degree at 0, so on and so forth, until we cannot find any nodes with in degree at 0. Yeah, so regarding this part, I think we are pretty clear. And regarding the first part, generate a graph, so how to do it. So actually, I think this one is also pretty clear to me, because when we just compare the so consider how we do the comparison between two strings. It's like if the first character is the same, then we compare the second character. If it's the same as well, then we compare the third letter. So on and so forth. So based on the order, we can see that we can extract the first vertex of the graph, which is T to F. So on and so forth, we can generate the graph and the corresponding in degree for each node. But for this one, do we need to, so I'm thinking, do we need to compare just the adjacent two words, or maybe compare the first word with all the words coming after it? So I think, I mean, we could do it. We can do the comparison between the first word and all the words coming after it, so on and so forth. But I think it's a waste of time. That is because so take this as an example. Let's say we generate W to E, W to R. It doesn't really make too much sense, because we have the vertex from W. So we have the vertex from W to E generated by this two adjacent word, and we have the E to R generated by this adjacent word, those two adjacent words. So it is for sure that we have W to E to R, so we don't really need to generate the implied rules from W to R. So I would say if we just compare the two adjacent words, it is good enough for us to generate the topology graph. So let's see what is the runtime for it. So regarding the regarding the first part, what is the runtime for it? The runtime would be okay, so suppose the average length for the words for word I, let's say if it is equal to L, then there are n words. So the first part, this one is going to be ln, because we compare the two adjacent words. And then for the second part, sort, so for the sorting, it is mainly about finding the in degrees with 0, and then try to remove it from the queue. So by the way, I think we could use BFS, which is based on queue as the underlying implementation, and then remove the in degrees for the adjacent nodes. So I would say this one, it's mostly based on the number of the edges, the number of the vertex in this graph. So what would be the number of the vertex here? So I would say the number of the vertex is actually linear to the number of the words, because we are generating one vertex from two adjacent words. So I would say a runtime in total, I would say the first part takes a bigger one. I would say it is OLN regarding the runtime at this time when I see the solution. So after we talk about the solution with the interior, the next part is about coding. So for coding, we care about the correctness of the code, of course, and also the readability, and of course don't be too slow for the coding. So let's get started to do some coding work. So the first part is about generating the graph and compute the integers. So let's say we will use a map from string to integer. It's not string to integer, it's character to integer. So this is a integrate new hash map, and the other one is the graph. So the graph is from character to a list of the character. Sure. So this is the graph. New hash map. So first of all, we need to compute the integers and the corresponding graph. So first of all, let's initialize it let's initialize the two maps. So first of all, let's see. Okay, so for string words, for character, say in word dot to call array. So integrate dot put c as 0. Okay, so if graph doc, if not graph contains the key character, then we are going to say, okay, graph dot put the c and new linked list character. Okay, so that finishes the initialization of the graph and the integrate. The next step is about actually generating the topology graph. So we are going to visit the adjacent words. So first of all, I is equal to 0, I is smaller than words.length -1 plus I. So let's say string word 1 would be equal to words I, and string word 2 is equal to words I plus 1. So so if I think there's some special cases. So for example, if the two words are AB and then another one is ABC, AB comes before ABC, but there's actually there isn't any useful information here, because that's mostly based on the length when you think about the string comparison, because the first one, it is shorter than ABC, but it is the prefix of ABC, so it comes before it. So this one is not really useful. So let's say if word 1 dot length is smaller or equal to or 2 dot length and word 2 dot starts with word 1. So we can simply continue this. So otherwise we can actually extract some information from it. So first of all, so we will have I equal to 0, I is smaller than mask dot min word 1 dot length and word 2 dot length, and then we plus the I. Alright, so we see, so now we do a character by character comparison. So if word 1 dot car, maybe we can just for simplicity we define car C, C1 and C2. So word 1 dot car at I, and car C2 is equal to word 2 dot car at I. Alright, so if C1 is not equal to C2, so that's the time we generate the relationship. So that's a piece of useful information. And so here we need to first of all generate the in degree. So in degree dot put okay, so let's see, what if there's already such a relationship there. So if there's already such a relationship there, we don't actually need it. Okay, so actually we need to define the map as character as a key and the set of the character as a value. Alright, so if it's not equal, and if not graph dot get C1 dot contains key. If it doesn't contain C2, then it's time we need to update the in degree map. So we are going to say, okay, in degree dot put in degree dot get C2 plus 1, and the key would be C2. Okay, this is the in degree, and then we need to also set the graph. So it's graph dot get C1 dot add C2. Okay, so now we have, so after this we need to break it, because all the information coming after that would be useless, because the sorting is just based on the comparison between C1 and C2, the first different character. So let's see. Alright, so let's see if so I think this part you have already finished generating the graph and the in degree map. The next step is about sorting. So this one is about generate the graph, and this part is about initialization, and then the next part is about topology sorting. Okay, so topology sorting, how to do that? We are going to define a queue of the of the nose. So we are going to define the queue, the character. Let's say it is a queue. Use linked list as the underlying implementation, and then what should we do? Should we? Okay, so what should we do? So the first one, yeah, I was thinking after we define the queue, I think it's pretty much just we get all the nodes with in degree as 0, put it there, and then do the BFS on top of it. So I'm thinking what I'm missing here. So if suppose there is a queue defined now, okay, so let's say the first step would be finding all the I think we may need to define a return values here. So let's say the string is so the string is the let's say the sequence. Let's say it is called sequence. It will be initialized as empty, and then the first step for us to do is to find all the in degree with 0 nodes. So for we are going to iterate through the for characters e as the in degree dot key set. Okay, so if in degree dot in degree so okay, so I think I have some typo here, so it's in degree all right. So if the in degree dot get c, what? Okay. There is some. I don't know why. I cannot type the thing here. It's really weird. Let's see. Okay, so I can type here, but I cannot really type in this page. Alright, so let me copy paste it and then reload this page. It's weird for my mic. Okay, glad we have the code still. Okay, so in degree dot get c, if it is equal to a 0, then we will need to put it into the queue. Dot put dot add the c into it. So this is the first step, and while q is not equal to so while q is not equal dot is not empty, then the first step for us to do is to generate the first thing for us to do is to pop the list of the nodes, list of the characters within degree at 0 from the queue at this moment. So we are going to say, okay, so list of the characters would be so this is the, let's say just cars as new linked list. So and int size is equal to q dot size. Okay, so we're going to say okay, the okay, so in I is equal to 0, I is smaller than size, and plus plus I. And you're gonna say cars, so car C is equal to Q dot pop pull the character, and we are going to add dot append. I think it's add. Okay, so add the C, and also we are going to say, okay, sequence is plus equal to the C. Sorry, plus equal to the character to string, or maybe you can define it as a string builder. Sequence as new string builder. Okay, sequence dot append the character, okay, the C. Okay, so now we append it and we add it into it. That, I think that's it. And the next step is for us to do we need to actually keep the cars? Actually, when we pull the character, we just need to update its adjacent node for the in-degree map. So for this one, we just need to say, okay, find all its adjacent nodes. So it's car C adjacent car is equal to what's that, the graph dot get the C. Okay, so find all of its adjacent character, and we are going to update the in-degree for it. So the in-degree dot put adjacent car, and the in-degree dot get adjacent car -1. Okay, this is the same, so we actually don't need to keep this cars here. So it's not empty. So first of all, we generate all the we pop all the things from the queue, and the next step is actually for us to see if okay, so we can do it here actually. So Jason knows for, okay, so we are going to so we update its adjacent nodes. We update the adjacent node into it. Okay, so suppose I update the in-degree of the corresponding node. I think it's time for us to also update the queue with if the in-degree dot get the adjacent car. So if this one is equal to a 0, then it's time for us to put it into the queue. It's queue.add the adjacent character. Alright, so now we should be pretty much done about this, and it's time for us to return it. So before returning it, we need to see whether it is a valid answer. So if sequence dot size or length, maybe. Okay, so a length is not equal to the what is that, the in-degree dot size, then it would be a invalid answer, so we return a empty string. Otherwise we return the sequence dot to string. So we are pretty much code complete with this, and so it's not the last step in the interview. So remember, we always need to think about doing some testing here. So for testing, there are two things. First of all, it's about to do some sanity check about this piece of code, and the other thing, like for sanity check, is mostly like going through an example, explaining how it works, and at the same time take a look at the correctness. And after that, you need to come up with different test cases to make sure that you have good enough test coverage. So let's see. For this one, let's go through this example. This example. So for this, we are going to first initialize the in-degree and the graph. So first of all, we will put all the in-degree, for each character we are having the in-degree as initialize as 0 for each character within the words. So it will be w equal to 0, r equal to 0, and t equal to 0, and f is equal to 0, and e is equal to 0. Okay, there are 5 characters. Okay, and then the graph would be so we will compare so we will also have the things like w, and it is going to be empty thing, r a empty thing, t empty, f empty, and e as empty. Okay, so now we have that, and we need to draw the graph using the code here, the generic graph code. So we will say, okay, we got the 2 adjacent words if it's the length is it's not like the first word 1 is a prefix of word 2, then we will, let's see, so so we will compare the character by character for the 2 adjacent words. So we will compare w is equal, then we don't care about it. So r is equal, we don't care about it. So the first different character for the 2 adjacent words is t and f. So we are going to update the in-degree for f as 1, and then for the graph we are going to put so we are going to have it actually graph.get c1 dot add c2. So it's like we have a edge, we have vertex from t to f, okay. Let's see, so we are going to update the in-degree for f to have it +1, and also the graph would be have an edge from t to f, okay. And similarly we will do w and e. So w so the degree for e will be 1 now, and there will be an edge from w to e, okay. And then the next thing is we compare r with t. I say that t in degree is 1, and then there is a edge from r to t. And the next thing is we compare e with r. So r in degree is equal to 1, so edge from e to r. Alright, so Okay, so let's see. So let's step into the next part, which is the topology sorting. So you have a queue with the in degree. So first of all, we will initialize it. We will put all the nodes with in degree as 0 into it. So we are going to say, okay, queue currently contains which one has, okay, so it is W. So, and after that, okay, and also we have the sequence, which is empty. And after this part, it is a while loop. So first of all, we will, so currently the size of the queue is equal to 1. We will pull the character from it, and then append it to, we pull it, and then we append to the sequence, and then we find all its adjacent nodes based on the graph. So W, there is an edge to the E, and so there's an edge to the E. We are going to update the in degree for E, and then the in degree for E is 0 now. And if the in degree is equal to 0 for E, so currently it is equal to 0, we are going to push the E into the queue. And similarly, the next step, we are going to pop E from the queue and append it to the sequence, and also update the in degree for the in degree for the adjacent node, which is R here. We're going to update R in degree as 0, and then we put R into the queue, and then we find that and the next round within this while loop, the in degree for R is 0, then we pop R from it, and I think, yeah, so yeah, and then we pop the R from it, and then we find the adjacent node, which is T. Update the in degree for T as 0. Since the in degree for this T is 0, then we put this into the queue, and next step we have pop it from the queue and append to sequence, find this adjacent node, which is F, update it with 0, and then we push it into the queue, and then we pop the queue from it, and we see that there's no adjacent node, so that's the end of this while loop. And finally, if the sequence length is equal to in degree size, then we return the sequence .toString. Okay, so I think it should work for this one. So for this one, I think it is going to return empty string. That is because there's no, after we generating the topology graph and also the in degree map, there's no node with in degree as 0 actually, because there's an edge from Z to X. We are going to for sure update the in degree for X to be 1, and then X to Z, so the in degree for Z is equal to 1 as for, at this moment. So at this time, so at this time we are not actually adding anything into the queue in this step. So for this example 3, I think it should also work as well. So let's give it a try. So in degree dot so line 18, oh, it's get C. Okay, it's a typo here. So so line 63, I is equal to 0. Okay, so it's some typo here, so it should be, we use J actually, so it should be J, and yeah, Okay, so graph C1 contains cannot find the symbol, so graph dot get, so the graph is character to set, so it's graph dot so line 67, so graph dot get C1 contains, maybe it is just contains. Okay, so line 68, so in the original get P2, okay, so it is complained that in the, okay, so it's in, add an extra E here, typo here, so okay, so a lot of typos, 79, so it's a indie gray again. Okay, so now we have fixed all the typos, and let's give it a submission. Okay, it's wrong answer, let's see why. So we have ABC and AB, and output is ABC at this moment. So output is ABC, but we actually expect it to be a empty string. Oh, that's because so yeah, I think that's not valid, because definitely AB should come before ABC. What should we do? If I would say that's definitely some invalid input. And what did we do? So I think what we did is this part. Alright, so what we did is when we do the comparison, we should so this one, it doesn't. Okay, so okay, so word 2 starts with word 1. This is definitely invalid thing. And then when we do the comparison, we see that the okay, if C1 is not equal to C2, okay, so if this one, so when we do the comparison, okay, so maybe it is if so if well, if word 1 dot length, okay, so if okay, maybe you can add an if branch saying that if word 1 is, so if word 1 dot length is larger than word 2, and the word 1 that starts with word 2, then that's definitely something invalid, and then we just return empty string. So I think this one, I think it should, yeah, I think it fixed that kind of problem. Yeah, so I think that's it for this coding question. Yeah, I think I definitely made some small little corner cases there for the invalid input. So definitely think about setting up some edge cases like that. So I would say, first of all, example 1 is a good one, and example 3, like an invalid one, would be a very good one. And also think about some test cases like that which failed our code there, setting up that kind of test cases to make sure that every branches have been reached. And that's it for this coding question. So if you have any question regarding this puzzle, please leave me a comment. And if you find this a bit helpful, please give me a thumb up, and I'll see you next time. Thanks for watching.